Introduce yourself. I don't think I'll do a better job than you do. So thanks again. Thanks, everyone.
Thank you, Padma, and thank you, everyone. Really happy to be with you all tonight. My name is Eden. I've been with Google for the last 2 years, and previously I was part of Microsoft, so I have a warm place in my heart for Microsoft, even though they took the decaf green tea from the menu, apparently, or so I found out today. And my passion for the last almost 2 years has been with generative AI. When I joined Google, I saw there were tremendous things happening under the hood. That was pre-chat GPT. And I was amazed at the things I saw. And I soon realized this is what I want to do. Fortunately, things worked out quite well in that regard. And I want to share with you some of the things that we are doing in the Gen AI space. But this is not about Google. This is about the next step or maybe the next phase for large language models and what it allows us to do, whether it's in our private lives as students, as lifelong learners, whether because we're building certain products for customers, consumers, enterprises, you name it. Long context LLMs make a lot of really cool stuff possible, and that's what I want to convince you of today. Let's do a quick show of hands. If you absolutely know what we mean by long context LLMs, then raise your hand. Thank you for the honesty. The vast majority are either shy or need a bit of explaining, so that's great. Let's talk about context then. So the context window of a transformer, we're talking about transformer architectures, these GPTs, Geminis, Claudes, and so on. The context window has a very simple definition, and that's the number of tokens that your LLM can process. Sometimes we'll call it the sequence length, but for our purposes, it's the same. What is a token? Token is the basic building block of transformers. A token in many cases is about one word. Some longer words, maybe more than one token, but we'll think of tokens as words. LLMs are what we call autoregressive generators, which is a fancy term to essentially say that they generate one token at a time. They predict a token at a time. So if you look at this diagram here, we start with a prompt that we provide to the LLM, whether that's what we're typing on a chatbot, maybe this is something that's programmatically generated. That is fed into the LLM, but it's fed into that context window. From there, the LLM performs inferencing on it to predict the next token. We get an output token. And now we have the original prompt plus one more token that was generated by the LLM. And that is fed back into the LLM to generate the next token in the sequence. And that repeats itself until the LLM decided it has had enough. And it will generate a special token that tells the program to essentially complete the inferencing process. That's why we call it autoregressive, because we generate one token at a time. Interestingly, LLMs are completely stateless. What do I mean by that? Of course, the model itself has been trained on a vast amount of information, so it has some knowledge of the world, a lot, in fact. But other than what it comes with from the factory in terms of its trained knowledge, the only way for the model to take notes during the processing stage is by outputting things and thinking about those things. So what do I mean by that? Think of chain of thought prompting. You've probably seen these prompts that encourage the model to think step by step. The reason they tend to produce more accurate and more correct results is pretty simple. The model takes notes as it thinks about the problem. It decomposes the problem into steps. And as it continues to predict the next token, each time it does that, it reflects back on what it has already produced. And that helps it stay on track, follow a certain procedure or algorithm, and ultimately end up with a conclusion that tends to be more useful to us. Now, why is this important? Because both the prompt that we originally provide to the model and its thinking process, all of these have to fit into the context window. And if the context window is longer, we can provide the LLM with more complicated tasks, if you will, but the LLM can also think more and produce more output for us. So far, so good. Why am I here? So the early LLMs had really small context windows. GPT-2, which was launched about 5 years ago, to no fanfare at all, nobody heard about it back then, had a 1,000 token context. GPT-3, a year or two later, 2,000. I think we have some technical issue. You don't see the screen? Okay. We should move to wireless, I think. So GPT-3 still had a pretty small context window. And in fact, most of the LLMs that you will use today have about 16,000, maybe 32,000 tokens. And that limits how many things we can do with the LLM. So for example, if I want the model to produce a book, well, most books are more than 30,000 tokens. So I can have the model produce a few pages of the book and then a few other pages, but every time it sort of forgets what the other pages were because it has no memory. Remember, it's stateless. So it limits how much input we can provide, but it also limits how much output. Now you might wonder, okay, so just make it bigger. What's the big deal? And as it turns out, this is much easier said than done. If we go back to the classic transformer paper from 2017, Attention is All You Need, this defines the transformer architecture as we still know it, and it defines something called the self-attention mechanism. That mechanism tells us that for the transformer to do its magic, it needs to consider every token in the sequence against every other token in the sequence. It needs to think of all the tokens in terms of pairings. Let me try to visualize that. This is from a nice tool called Comet ML. It helps you visualize ML experiments. So here we have a sequence, a prompt, think of it that way, or a part of a prompt. Many people dislike Steve Jobs while acknowledging his genius. And what we see here is that every token has this line with every other token, but the lines don't have the same width. So the width of the line, the thickness of it, describes how related each token is to every other token. That's kind of the secret of the attention mechanism, the secret sauce. Computing these lines is essential to making this thing work. And we have to do that between every couple of tokens. You might notice that there are also several colors there. Each color denotes a different attention head. There are multiple attention heads, basically. So we're not just thinking about every token with respect to every other token. We're kind of thinking of them from different angles. Every head assesses something, a different attribute or feature of each of these tokens. And all this needs to be produced every time we want to predict the next token. So if we have n tokens and we have to create an attention matrix for every token against every previous token, that's the order of n squared. If we want to increase the context by 4 times, now we have to compute 16 times as many attention scores. These attention scores are the lines that we saw between every pair of tokens. So that explodes quite quickly. Now, to give you a sense of how much work has to go into computing these lines, computing just a single line requires thousands of multiplications and additions. We do this for every pair of tokens, for every head of the transformer. GPT-3 has about 100 heads, just to give you an idea. And we do this for every layer of the transformer. With GPT-3, we have 100 heads too. I think it's 96. And this is done every time we want to generate a token. So there is an awful lot of work. And if it grows quadratically, that's not a nice thing. That's why context windows have tended to be very, very small. Fortunately, there's some good news. This is one of the biggest challenges in the large language model space, and that has attracted a lot of attention, no pun intended, a lot of focus, let's say, from ML researchers to find creative ways to address the context window problem, to make it larger without being penalized in terms of the time and the effort and the energy that this requires. By the way, the next slides will be much less technical. So if this is too much for you, I promise you salvation is coming to us very soon. So what are researchers coming up with? There are hundreds, if not thousands, of papers on this topic, but I would say 4 major categories of improvements to transformer attention. So the first one is, well, maybe we don't need to think of all the different pairings of tokens. Maybe we can keep a sparse attention. Maybe we can sparsify the attention matrix. We could say that some tokens are more important than others, so maybe we can skip certain tokens. Here's an example. If you take the word of, the preposition, the word of, house of cards, for example, of relates to house, it relates to cards, but it probably doesn't relate to anything farther than these 2 immediate tokens. So do we need to compute an attention between of and some other token 100 words later? Probably not. And these things, we don't need to program them because this is a meetup about machine learning. So it is learned in the process of training. The LLM can pick up on these patterns and basically realize that certain tokens might be skipped in this process. So that's an idea of what sparse attention looks like. Another wave of improvements centers around hierarchical attention. So think of computing attention maybe at the sentence level. So you take a sentence, you create a representation of it in some hidden space as we do for tokens, but you do it at the sentence level. So there are fewer sentences, so the matrix isn't that great, for example, in size. So that's another way to optimize things. Memory compression, that's yet another approach. A recent and very good paper on it comes from Google called Infini Attention. It's a proposal for how to extend attention to infinity. I don't think it can go that far, but it's still quite interesting. And last but not least, this applies not just to attention or to context windows, is optimizing LLMs in general. I'll give you a few ideas of what everybody is doing in this space. You all probably know that these models have billions of parameters. These parameters are essentially weights, and we used to use 8-bit or 16-bit weights. Now we're starting to move to smaller and smaller weights because it looks like even though we lose some precision, it tends to be good enough in many cases, or we can compensate for it in other ways that are still overall cheaper. If the weights are smaller, a lot of these calculations that we mentioned are also quite easier to do. You need less memory and so on. That is one avenue. Other avenues are to look for ways to move less memory around. The GPUs usually compute on their cache, but they also have VRAM or DRAM, which is where the model is stored at all times. They need to shuttle the memory and the parameters back and forth. There are many clever ways to reduce the amount of copies that are needed. So all these things combined together are helping us make some pretty important improvements. Let's see what these improvements are. So last July, we had the very first model that claimed to have a long context. That was Claude 2 with 100,000 tokens. Have any of you used Claude, by the way? Okay. Their marketing people have a lot of work to do, apparently. But it's a great model. I love it. A few months later, GPT-4, OpenAI finally came up with their long context option. They offered a variant of GPT-4 with 128,000 tokens. I think the previous was 32,000, so a 4x improvement. Claude 2.0 followed, doubled the previous one to 200,000. So it all looks quite good in that sense. Claude 3 is a very good model. It still has 200,000 tokens. But what seemed to be the case was that when we pressure tested these long contexts to see how useful they are, they underwhelmed us. And one way to benchmark these long contexts is what we call a needle in a haystack. That's an interesting benchmark. So what is the needle in a haystack benchmark? Imagine that you have a haystack, a large amount of data that you feed into the prompt. You can go all the way and feed the entire context window. So in this case, they tested it up to 200,000 tokens with Claude 2. And then we take a needle. Again, we lost video. Okay, sorry about that. Then we take a little needle. The needle would be some random fact or piece of information that could be important. Still no video? Okay. Do we have any techies? Oh, it's back. Okay, I just shouldn't touch things. So we take a needle. The needle could be a critical piece of information, and we ask a question. The question should be one that you cannot answer unless you found the needle in the haystack. That tells us whether the LLM is truly attending to the entire context or it's missing some critical information. Now, if I'm a doctor and I rely on a large language model to look through a medical file and sift through it and pick up some vital piece of information, if I cannot trust that the large language model will do it well, I might as well not use it at all. So these types of benchmarks have real-world applications. What this tells us, the map here, is that as we go right, as we add more and more tokens to the context window and reach 200,000, the limit, depending on where we put the needle in the haystack, which part of the context, everywhere you have a red cell, the model failed to find the needle. So that wasn't really great. And so what is the usefulness of long context models if they fail to look through the context carefully? Okay, this is where we come, Google. So in February, we announced Gemini 1.5 Pro. This is Google's first long context LLM, and it is a 5x improvement in size over the previous one, which was Claude, so 1 million tokens. In fact, internally, we use it with up to 10 million tokens, and it scales very, very nicely. And maybe the most important thing, the needle in a haystack benchmarks, we see up to or over 99% recall rate. So that is the rate at which the model succeeds to find the needle and to use it to answer the prompt correctly, even at 10 million tokens. So it is nearly perfect. Not only that, this model itself is of very high quality. In many ways, it actually meets, sometimes even exceeds the Gemini 1.0 Ultra model, which is a larger and more costly model to run, and it's natively multimodal. That means that it can parse not only text, but other modalities, visuals, audio, and so on. Okay, so we got 1 million tokens with this. What can you actually do with it? So 700,000 words. This is roughly the length of Tolstoy's War and Peace. Not a fun thing to read if you have to file a book report the next day. Or 11 hours of audio recordings, not just the words in the audio, but really the entire nuance of the waveform. 1 hour of video can fit into a large context window like that. You might be wondering, well, video, you're talking about tokens. What's the connection? There is a way to tokenize images. So we can take images and we can turn them into tokens and process them. And I wouldn't tell you about it if it didn't work as well as it does. It actually works very well. So we can tokenize not just words, but other forms of data. Or we can feed an entire project of 30,000 lines of code, OpenSSH, Git. These are pretty famous open source projects, and they are under 30,000 lines of code. So we can feed that entire project and ask questions about it. If you look at the model card for Gemini 1.5, which I think is a very readable document and not very long, this is basically the white paper for the model. It has a few examples of what this was tested on. So this is an example of something cool we could do with it. We can give it a long book in the prompt itself, just kind of drop a PDF. This is Les Miserables, probably butchering the French pronunciation. It's a very long book from Victor Hugo from 1850s or something. And we can include this hand-drawn sketch, both in the same prompt. It's multimodal. And we can ask it, find the part of the book, a passage described by this sketch. And it can do something like that in a matter of seconds. So in this case, it's realizing these are two silver candlesticks or candlesticks, and it outputs the passage and highlights the relevant part of that. So imagine giving a task to somebody, telling them, here's a book, here's a sketch I've drawn, tell me which page this is from. It could take many, many days to do that. So we can cheat with book reports, essentially. I'm not sure if this is a great pedagogical practice, but I promise you there are more or less controversial things you could do with long context. So let's look at things that we've already been doing with LLMs, but we can do in a far superior way. Summarizations is one thing. So far, we've been limited by how many pages we can feed into the prompt. There were various ways to work around it. Why don't we just break the long content into smaller pieces, and then we summarize each one, and we make a summary of summaries? That doesn't tend to work very well because there are often duplications or things would be missed. No need to kind of do this prompt engineering anymore. You could just ask exactly for what you want and get a higher quality result. As we saw in the example, we can feed in some kind of content or document and ask any kind of question that we want about it. So it's almost as if you ask me, and I use it all the time, it's like interviewing the author about their book. Writing completions is something that LLMs are great for. In fact, this was the original use case, just to complete a sequence of words. But it makes a big difference when you can look back at the entire content, not just offer a completion based on the last 10 pages. But if I wrote 200 pages of a book and I want the next 20 pages, the model can look back at the entire piece of work and suggest something that's much more coherent. Multi-turn conversations. So these are dialogue systems like chatbots. The early chatbots, based on models like GPT, used to forget what we talked to them about after 30 minutes of conversation or something. Remember, you had a 2,000 token window. There's not much that you can fit into that. Now you could have chatbots that not only remember the entire session, but in fact can remember the entire history of sessions you've ever had with that model. So much better for personalization and just much more trust-inducing, I would say. Then we have some entirely new possibilities of things we couldn't do before and that we can do now. So one idea or one set of options is just to produce long-form creative writing from scratch. So it could be something like, here's a manuscript in English, translated to Arabic. It could be something like, here is a prompt for a screenplay that I want. Write the entire screenplay, or write a novel, or prompt to book, or anything really. It can produce hundreds and hundreds of pages that fit into the same context window. And this means the LLM can actually remember what it wrote as it's writing it. That's a big problem right now. The LLMs well, not today, but yesterday, could only remember about 10 pages worth of text. So it's very hard to get them to write high quality content beyond that limit. Code reviews and assessment. So we talked about the ability to consume an entire project. Because LLMs have so many internal iterations in the way they process information, this translates into an ability of a language model to follow, to trace, to kind of simulate an entire control flow through a very deep call stack. So you can feed the LLM with a challenge like, given these files, this code, this project, I'm running this input and I'm getting this output, and I'm not sure why this is happening. Can you help me debug it? And it can absolutely save you a lot of work. I'm not saying it's going to find the bug right away, but it can analyze the project perhaps more deeply than you can expect. Legal contract analysis, that's another entire category. One of the things paralegals hate the most is the back-breaking labor of having to go through a lot of past contracts as they renew a contract to find inconsistencies or clauses that have to be renewed and so forth. You can just dump 40 different contracts and ask the LLM which of these items contradict each other. We're working on a renewed contract. What should we pay attention to based on past contracts? Or if you have multiple different customers and you have a different contract with each one and you want to ensure everybody gets the same treatment, you can use systems like that as well. And last but not least, I think last but most importantly, LLMs still have a problem of hallucinating. I think it's getting a lot better, and I'm super optimistic that we'll get this sorted out in the next 3 years. But for the time being, it's not always the most trustworthy source of information. However, it works really well if we ground them. So if we provide some reference and we tell them, based on this reference, how would you answer this or perform this task? They tend to do a much better and more reliable job because they can point to the reference and we can even double check them or use another model to double check them. The way we do it today, or used to do it, is with RAG systems. So we had a retrieval system that searched for the relevant reference, fed it into the prompt, and this is how the LLM would get its grounding information. This is a pretty complicated thing to do, and sometimes the retrieval wasn't, in fact, the most relevant part of the reference. Sometimes you just needed more grounding information than you could fit into a prompt. Now you can basically drop in the entire company policy, say, every time you run a certain task, and you could ask the LLM, based on this policy, we want to publish this PR statement. Is there any violation? Or we want to send this email to a supplier. Is anything here in contradiction with our policy? You could do that very simply, very cheaply every time you want to be sure you're not in violation of anything. So lots of options here. And I should say, this is what we think this will be used for, but the fundamental thing is long context LLMs are a capability. What we do with it, how we use it, this is up to all of us to figure out. There are countless other options and use cases. So you're no longer limited as much by the length of the prompt. You're no longer limited to using retrieval systems and so on. There are much simpler ways, just kind of drag and drop, and that's what I want to show you in the next demo. So we're going to see Gemini 1.5. I think it's not the only long context LLM. It's just 5 times longer than the rest, but more will come. Let's do it interactively. So I want 2 volunteers who sometimes follow the stock market. Or more than sometimes. Do you want to be one of them? Okay. You're the first volunteer and you're the second. Can you pick a publicly traded company that you think most of us might be familiar with? NVIDIA. Okay, good pick. Microsoft and NVIDIA. Okay. You know what? I want them to be a bit more distant. So pick something, but not from the tech space. Chipotle. Okay. You have a great taste. So let's do the following. Before I do that, I'm going to tell you what I'm going to do. So I'm going to take a few annual reports of these companies. These are usually pretty long PDFs with a lot of information. The first thing, we will do something like a needle in a haystack test for Gemini. We will pick a random fact. You will pick, not me. We'll find a random fact from the NVIDIA earnings report or the annual report and just throw that PDF into Gemini and see if it can find the needle in the haystack and how well it does that. So that's going to be our first step. And I think on time, we have like 15 minutes, maybe? Okay. Let's do another interesting thing. So I took the 23 report, but let's go way back because apparently they have older statements too. Let's take the 2011 or even further back. No, okay. I think yeah, this is the oldest one. Okay, 2008 was it? 11. Okay. Okay, and while we're in the 23, so this says it's not that long, 169 pages. I don't know how many tokens, but we'll find out. Let's pick a random page. Who wants to offer a number from 1 to 169? Okay, I hope it's not going to be a bunch of, yeah, this one. Yeah, you want this one? 42? Okay, 42. Okay. Again, directors. Okay, we'll stick with one of them. Okay, I think we can ask something like, which of their directors is, let's see what this guy did, was on the board of myocardia? I think that's a pretty random question, right? Okay. Okay. So this is the AI studio that every developer can use. And I think right now it's free for Gemini 1.5. So if you want to experiment, you should do that. But I think it's free. Don't take my word for it. Check it yourself. Don't come to me with invoices. Okay, so it's a 40 megabyte file, but really we're going to extract the text from it. It's going to do it itself. Okay. I'm not a great one-handed typer, but let's see. By the way, is this large enough? Can you see? Okay. Based on this document. Does anyone remember the name of the person? Mark Perry. Yeah, I think this is pretty much what we asked. Let's see. Which NVIDIA director was, okay. It's 136,000 tokens. And I hope the service is up. It's taking some time. Usually it's a bit faster. Okay. Mark Perry was on the board of myocardia. Okay, that's the correct answer. Let's see, which page is it from? Please provide a reference. We want to make sure it's using grounded information. And notice I'm asking it some very poorly phrased questions, like which page is this from? This is a very informal way to communicate with anyone. But what I like about large language models, they get it. You really don't need to be very prescriptive. So the answer, while it works on it, is 42, but it might tell us 23. Let's see how it actually approaches this. Page 42. Okay. So I think it did a good job. Now we have Chipotle, right? Let's not forget about them. How long it took to do that? I don't think it shows you once it's done. I think it was about 30 to 40 seconds, kind of my feeling. Yeah, this is, you see the answer? So it says page 42 because I guess it looks at the PDF pages. Yes, I think sometimes it can return those pages. I'm not sure why it would often or potentially choose the PDF versus the embedded page number. Yeah, why do we have a dangerous content? Well, okay. It's a sensitive model. We have to respect that. Okay, let's do, you know what, before we go to Chipotle, let's do something fun. Remember, we have another, we can ask any question, and that's what I will do now. So I'm going to attach the 2011 report in addition to 2013, which was already there. And what I want to ask it is, what are the big uh, business drivers of NVIDIA's business in 2023 that were barely or not at all mentioned in 2011? Any crazy guesses? So this is a more realistic use case in my view for long context, because we're providing multiple different documents and we're expecting the model to perform kind of cross-document reasoning and synthesis. This is what we were taught to do at school and used to spend a lot of time on. Yeah, so good point. This is exactly the type of things we really see long context shining on. And as it works, let's pick up the Chipotle ones, right? I would say if the cost was prohibitive, we wouldn't have it. The fact that it exists tells you that it's doable. But that's the reason very few companies, in fact, none other than Google, to my knowledge, currently offer a long context LLM. Okay, so Chipotle, we got that. Okay. It's not as nice as NVIDIA, so they really need to work on the styling of this. Yeah. I think the other was a 10K. Yeah, they're both a 10K. Whoa, okay, so Gemini is on a roll. New major business products and lines for NVIDIA, data center platforms and AI. I think that's the right call. Automotive AI, who knew about this in 2011? And so a good analysis, Tegra chips were starting to be adopted in cars for infotainment and navigation, but autonomous driving was in its infancy. And now they got all these other products. Omniverse, I don't even know what that is. Never mentioned in 2011. I probably still live back in 2011. Now they have the Omniverse cloud. If anyone could tell me what it is after 3D metaverse, okay. And of course, Gen AI and language models. Deep learning was in its early stages. The concept of Gen AI was not present. So I think it did a fine job here. Last but not least, we have Chipotle, right? We're a bit short on time, so I just want to make sure we are, yeah, a quick one, yes. No, none of what you see is audited. So I think every AI lab runs a lot of experiments and tests on their products. But at the end of the day, one thing we have to remember with generative AI, what you're getting is something you are responsible for, how you use it, and it could be factually incorrect, absolutely. So we have to be very careful. This is why the grounding aspect of this is so crucial, because it allows us to go and confirm that what we're seeing seems to make sense. But absolutely, we should not take it at face value. We have to double check and triple check. Let's add Chipotle to the mix and ask it to find three common things between these two businesses, NVIDIA and Chipotle, that are not obvious. Does it matter? If anyone knew the answer, they would lie to you because we don't really know how the model thinks of this. What I can tell you is that it is tokenized in a way that is different from a non-capitalized word. So the signal is absolutely being maintained and retained. And I do think it makes a difference, yes. It's not okay. So is the attention score different? A capitalized token, in my view, would actually be embedded into a different representation in the model's space. So it has a different meaning, in fact. That would be my guess. However, maybe the front end converts it to lowercase before we see it. I don't actually know whether that's the case or not. Okay, so 3 common things between NVIDIA and Chipotle. Reliance on a complex global supply chain. So avocados and foundries apparently are both global goods that have to be involved in the production process. So I think that seems to make sense. Facing risks of price volatility, shortages, that is true of many other things in the semiconductor space. Importance of technology and digitalization. So apparently Chipotle has a heavily invested in digital platform, online cataloging, ordering. Do you concur? Is that true? Does anyone know? Yeah? Okay, cool. What's that? This is all coming from Gemini Live. Yeah, because you guys decided it should be NVIDIA and Chipotle. And then the last thing, emphasis on talent management and company culture. People first culture. Apparently, both companies at least claim to have a pretty strong company culture and a focus on maintaining and developing top talent. So thank you very much. I think we're out of time. I wanted to do a multimodal one, but we have Mitesh next. Right, Mitesh, you're next. Okay, so come on up, and thank you all for your time. Okay, so you hear me okay? 2 questions. The first one, we fed the LLM with a publicly available PDF, right? Was the LLM already familiar with it? Because at the end of the day, if I could find it on Google, then I think our team that trained Gemini could find it too. So my first response to that is, does it matter? If it knows the right answer because either it was pre-trained on it or it saw it as part of the prompt, then, as long as it knows where to retrieve the information from and respond to the answer, then it shouldn't really matter. But to your specific question, my answer is, even if it saw it during pre-training, it probably didn't see it too many times, would be my guess. In order for neural networks to be trained to a point where they can really remember each and every detail from a long document, they need to be exposed to it many, many times. And I don't know if it was exposed to this document many times. Maybe the cutoff date happened before the 23 annual report was even published. And so I would tend to think, and we can actually test it, that if I didn't provide the PDF and I just asked this question, the odds of getting a correct answer would have been much lower. So that's your first question. The second question was about, yeah, right. So yeah, so from a technological point of view, when you use the LLM, you're not changing the LLM in any way. It is a static network. It doesn't change. It doesn't learn anything. The only time it learns is during the training phase, which happens at the factory before you ever have access to that model. That being said, every different AI lab has different policies with respect to what happens with the data you provided. Some might use it for training, some might not, depending on a lot of different factors. So if you want to be sure, you have to look at the license agreement.
GitHub, I think you mentioned about GitHub at one point in your. So if I upload a piece of code, and I say prompt, I said, optimize my code, clean it up, we'll be able to do that?
Yeah, I think I mentioned Git, not GitHub. Yeah. Yes, LLMs do a spectacular job at cleaning code and other forms of data, absolutely. Stylizing code in a consistent way. Yeah, I've seen them do much more complicated things. Well, GitHub Copilot is powered by a large language model, by GPT. So if GPT can do it, others can do that too. Yeah, absolutely. And GitHub Copilot is basically an application that uses an LLM. And so, yeah, it's a pretty simple use case. Every LLM can do that quite well. Yeah, questions? I talked to you in the back there while I was having pizza. So
you mentioned that the token length, the larger it is, the more accurate and less hallucinations it produces. Is there any way that token length is optimized over time? Is the ideal optimal token length, or it stays fixed the whole time, or any of the fine tuning affect the token length?
Thank you. So I think you referred to context window there, right? Okay, yeah. So yeah, so the context window, good question, actually. So there are two parts to my answer. Take Llama 3, that's a model that was released just a few weeks ago. I think Llama 3 has a context window of 16,000, might be wrong, but that's my recollection. You can't really change it. Once you use a given model, that's what you have. However, because Llama 3 is open source, the developer community has forked it into a different variant that I think is 100 or maybe even more than 100,000 tokens. So you could say, oh, you can, at least with an open source model or open weight model, we should say, because only the weights are really open, you can create a variant that has a larger token count support. But it doesn't work very well. And the reason it doesn't work very well is that Llama 3 was trained or pre-trained on sequences of, let's say, up to 16,000 tokens, because that's the context window. It means that during the training, it learned to establish these relationships between tokens that are no more than 15,998 tokens apart, because that was the limitation during pre-training. So now, even if you somehow manipulated the system to support larger tokens, it hasn't seen larger prompts. It hasn't seen such prompts during training. So I don't know if it would scale very well. What I would suggest is whatever the original lab kind of specified in their model card, you should assume that probably works okay. Longer than that, I wouldn't really trust that. Yeah, nothing after the pre-training phase of the model, including the fine training, nothing after that would do a good job or any job at all of extending the context window. Yeah, that's my opinion, at least. Yeah. I don't know anything about quantum computing, so I cannot take this question. Yeah. I can hallucinate, but you can go to some LLMs and get that too. Yeah. Microphone, yeah.
In your experience with LLMs, what would you recommend? Like, at what point should people consider fine tuning versus using the long context length, if that makes sense.
So the question is, yeah, you heard that. You had the mic. So I think the way to think about how to prime an LLM to produce the type of results that you want is first start with long context or start with prompt engineering. Maybe you don't need long context, but try to craft a prompt that solves the task that you have reliably and ideally affordably. It doesn't require a lot of tokens. If you're struggling with that and it doesn't seem to work well, then, and I'm assuming you took a prompt engineering course, otherwise, yeah. So assuming you know what you're doing with prompt engineering, I would try that first. If you're not getting the sufficient results, and the context window was the problem, as in you could have provided more examples, but you were limited by the context window, try a longer context LLM, see if that works. Only if that doesn't work good enough for you, then I would try reverting to other methods. That could be RAG, if you have a lot of data and you just could not fit it into the window, or it could be fine-tuning. Maybe it means, I don't know, pre-training your own model, but definitely start with prompt engineering first. And in most cases, it will do the job. What I see happening in many cases is teams start with prompt engineering, they get to a result that they generally like, and then it becomes a question of, can I afford to run this prompt again and again and again, because I need to pay by the token count. If they're not really happy with the economics of it, then they start thinking of ways to economize on it. Yeah, no. Yeah, very good question. So when we talk about so the question is, which demo did I not show you that I was planning to show you? And now I can make up literally anything because I don't have to prove it. But and the second question was about image generation. So let's start with the second one because it's easy. Multimodal LLMs do not generate images or videos or audio. They only generate text. They take as input these other modalities, but they generate text. There isn't a very effective way to generate images with LLMs. It is possible. The results are not that pleasing. So we tend to use what we call latent diffusion models or other kinds of architectures for images or video. So it's only images in, not images out. About the demo that I didn't show you, so what I was planning to do is to look for a video on an open kind of video platform. I think it's called Pexels. You would give me the subject for that video. I would look, let's say you said cars, so I would look for a video about cars. I would download it. Then we would pick a random spot in that video. We would pick up on something. So let's say it was a bus crossing a junction, let's say. And we would ask the model, go through this video and tell me at which point a bus crosses a junction, for example. And it would hopefully find that. And it's an incredible capability if you think about it, because sure, we can do that with ML, but they have to be very specialized on these types of vision tasks. And here with LLMs, we can now take arbitrary videos, ask arbitrary questions, and they're not so only about when does the red bus cross the street. It could also be about when in this dialogue are the two people in agreement. Okay, no words, no audio, just by gestures and stuff like that. So there is also an emotional aspect that LLMs are pretty good on picking up on. How many images can you upload? I would say just try it at home, seriously, because it will show you how many tokens you're using. But you would be surprised. You can fit in a very large number of images. Yes, everything is tokenized. Yes. Mm-hmm. Yeah. So essentially what the LLM looks at is not the image, but some kind of latent representation of what is in the image. Yeah. There is somebody who had the hand up, so yeah. No? Okay, people are scratching, so. Oh, yeah, okay.